back here. Okay, so the next thing on the list, we'll go over kind of slow, make sure everything's clear here, because this is kind of a big deal in programming. And I know a lot of people are taking the introduction class at the same time. I put a note somewhere in here about it, yeah. My original plan, before I knew who I was going to be taking the course, I was thinking this was going to be like the third level of object-oriented programming. So like you get introduced to it in the 140 class, introduced to the first couple concepts, mostly practice encapsulation. And then in the 200 level language specific course, the Java course or the Python course or C# course, the explicitly one language course, you would get practice with expanding encapsulation into inheritance and polymorphism, and maybe get introduced to interfaces and abstractions. And yeah, then I use the textbook that goes with this statewide course shell, and it seems whoever chose that textbook seems to have thought the same thing, because, well, the textbook had very brief reviews really of encapsulation, inheritance, and polymorphism, and talked at length about interfaces and abstraction, and even got into namespaces. So when I was putting my plan together, I was originally was thinking that this class would be mostly looking at the more advanced level of object-oriented programming. So we're going to back that off and kind of do a thorough introduction to it, because this is a big deal, and we want to make sure you understand this pretty well. It does take practice, and that's another thing about taking all the classes at the same time, right? Those of y'all in the 140, the 250, and 253 class, it's kind of like you're taking the introduction and 2 advanced classes at the same time and skipping over the intermediate practice level altogether. So we're going to stretch this out for a while. And then the other topic for this week, the exception handling, is an extension of object-oriented programming. So we want to make sure it kind of makes sense. Object-oriented programming, and that's a lot to write on the board. So I'm going to start off by putting the abbreviation I'll use. So I'm actually going to, on the board here, I'm going to write OOPS. Object-oriented programming, and then the S is just there to make it to actually make it a word. I guess you could think object-oriented programming software if you want the S to stand for something, but really just the normal anagram, except it's so close to a common thing we say, I'm going to go ahead and put the S in there. It fits really well with programming too, just abbreviate our main thing as OOPS. So this isn't an alternative. This isn't a different syntax we could use. It's not necessarily a syntax thing. It's an entire method for constructing our algorithms and really the tools we have to solve algorithms. So really what it is it's another methodology by which we can approach programming. Methodology for constructing tools to solve algorithms. I'll go ahead and add in here, which is better, and I'm going to write better in big capital letters, because which is better for humans. It's much worse for the machine. It's much better for the human. There's a trade-off, but it's not a trade-off we worry about because we generally don't mind how much work we put on pushing extra work onto the machine. Like if the machine has to do extra, that's fine. The phrase I like to use is if the programmer, the human, can do 1,000 times more at only a 10% loss in efficiency, it's well worth the trade-off then, right? We're gaining a lot by approaching programming with this different methodology, but we do lose a little bit in efficiency, which translates into speed. There's kind of some things to make up for it, but it is well worth the trade-off. So historically, it was developed in Norway back in the 1960s. But back in the 1960s, that's better for humans, worse for the machine. The machines couldn't handle it. It was too much. So it's probably the mid-1980s before the average computer could deal with the extra overhead that comes with object-oriented programming. But as soon as the, average computer could deal with that extra overhead, it pretty much immediately became the predominant methodology for programming, and has been ever since. So what I like to put.
So Chris, I'm sorry. Yeah. So Chris, so that's why it took us so long to get Windows.
In part, Windows could not have been done without object-oriented programming.
Right. And the machines couldn't do it until.
Yeah, the machines couldn't do it till then. Yeah, so like technically we could have done Windows back then, but we need the objects. And the picture I'm going to put up here hopefully makes sense. But yeah, that's a great example, Joe. That's why it took so long. That's why everything was text. Like in your SDEV 120 class, the menu-based stuff. You probably remember this, Joe. I remember working with the menu-based stuff back in the day. It's kind of a pain.
Yeah, menu-based, and I mean, if you look at DBase 3 and 3 Plus and 4 or whatever, it was all menu-driven, and it was clunky and.
Yeah.
But it did cool stuff.
Yeah, it did. It would do all this stuff. Typos made a big difference. If you made a typo, you might accidentally mess up your operating system and have to reinstall and start over. So there's a lot we gain from it. So we want to make sure and understand it because it is the predominant thing we'll use. And the reason why is we get to think like a human again. Because that's really what we're doing in the 100 level programming classes, right? The 120 and 140 class. We're learning to think in a different way so that we can feed instructions into a machine. Really the 120 class, but the 140 still is a lot of how to put algorithms together and choose the parts of our syntax and how to think in a way that works with the machines. But the biggest advantage of object-oriented programming is we get to think like a human again. So I always draw this picture. Has everybody had a biology class? I believe you have to have biology to graduate from high school. So you probably saw this picture there. That's not necessarily a college level biology class, or you might have seen it somewhere along the way. The tree of life picture. Is everybody familiar with that? It's a good example of the way that's kind of natural for humans to categorize things. What did I put on here? I'm not going to draw the whole tree, just a couple circles to point at. So at the root of our tree, we have just life form in general. Maybe I'll put life form instead of life. And write the word before I draw the bubble. That'll probably help with the, so at the root of our tree, we just call everything a life form. There's all these carbon-based stuff, all sorts of different things, but it's a life form. And we can distinguish life forms from things that aren't life forms, right? If you've heard of SETI, the Search for Extraterrestrial Intelligence, in the early days of SETI, they were getting things up and people kept asking them, how are they going to find stuff? And one of the early scientists, his grandmother stopped by to visit, see what they were doing and stuff. And they were expecting that question because people kept asking them how they were going to recognize it. And she had a way of phrasing it that was better than what anybody else had thought, all these brilliant scientists had thought of. And when they, conversation got to why she hadn't asked that question, she's like, well, I know what you're looking for. It's life. You'll recognize it when you see it. Life is squishy. And that kind of stuck around for SETI for a long time. Life forms are squishy. The things that aren't alive, we recognize that they're not alive. So we have that categorization that separates living things from non-living things when we look at biology. So on this side, I'm drawing the biology picture. And then, but that's kind of general. We want to make it more specific. So in biology class, we split that up into three main branches: archaea, bacteria, and eukarya. And it's a little bit more specific. There are distinct differences between bacteria and eukaryotes. Or just saying bacteria might not be specific enough for us. I have no idea how to spell the next ones I'm going to put here, but a couple of bacteria that you might have heard of, like E. coli is one type of bacteria, but they are distinctly different from Staphylococcus. I'm going to abbreviate that, the stuff that's always a concern in hospitals, but different types of bacteria. And we distinguish, there's still types of bacteria, so they're in that category, but they're more specific subcategories. Same thing with eukaryotes. One category would be fish, and another one, mammals. And fish and mammals have a lot of things in common, right? That's, well, a couple more steps up there, but eventually they're both types of eukaryotes, which is a type of life form itself. But we could also get more specific. I'll expand the mammal side out. And a couple types of mammals are humans or elephants. Everybody seen that picture before in biology class? It's usually a lot bigger, but the whole tree of life image. That's the way humans naturally categorize stuff. We start with our root, the just most generic category that includes everything. And we get more specific as we go down. But we can also think of it the other way and go back up, right? Like humans, fairly specific. Mammals, there are certain traits about a mammal, hair, milk, warm-blooded. Everything about a mammal falls under here. And these subcategories, like humans and elephants, those have all the mammal traits, but then they get more specific. Right? All those mammal traits of hair and wounds, so except for a couple exceptions, the mammals don't lay eggs, that have hair, warm-blooded, and all that stuff. And elephants and humans have all of that, but then we add more details, like walk on two legs, have opposable thumbs, or elephants really big, have the trunks, and it gets more detailed as we go down, but everything down the tree still is a type of it, where it falls above. So a human is also a eukaryote because it meets all those criteria. Or a human is also a life form in general, and the whole tree of life image. I usually feel it's okay to go ahead and assume everybody has seen that at some point, right? Maybe explicitly in a biology class in high school, but you probably came across the tree of life somewhere on your way through life so far. And that's the way humans naturally categorize things. So jumping ahead a little bit, and in object-oriented programming, when we go to organize the structure of our code, we end up with a picture that is very, very similar. So a common example I do is with animal objects. We might actually do this example before this week's out, but there's some categories about what our program would consider an animal. What I usually do in the example is adds a name, an age, and makes a sound. Is the criteria for an animal in some generic program to explain object-oriented programming. But we have this overriding thing that has all those criteria. But we can get more detailed versions. Sometimes there are expansions where we add stuff and add details, kind of like I was talking about with the human and elephant is expanding on mammals, everything it means to be a mammal, but then more stuff like walk on two legs, or everything it means to be a mammal, but then more stuff like has a trunk. So we can do that, or an object-oriented programming. Sometimes we just do it for a naming thing. Maybe a lion, for everything in our program, when it's called a lion, it's just a useful name, but it doesn't really add anything to that, just a particular detail about one type of animal. Whereas other animals, like maybe our program needs a cat animal. And so the default example for an animal that I always use is our generic sound. The default sound is going to be roar, which is fine for a lion, but that detail is not going to work for a cat. So we modify that a little and change our default sound to something appropriate for a cat. Or another animal would be like a dog. And we can add in more details. I don't know, some dogs wear bandanas. So that's a detail that other animals in our program wouldn't have. We often tie bandanas around our dogs' necks, but we don't necessarily do that on cats. We definitely don't do it on lions. They might let us, but nobody's going to try. So we took everything it means to be an animal and expanded that a little with more details. And we can do the same thing. Take everything it means to be a dog and expand that into types of dogs. Like a beagle or a pit bull. And everything it means to be a dog, but then some more details. The floppy ears, or the refined jaw strength and control, and just more details on top of that. So that picture is going to make a lot more sense later. I like to start off with it because this is a diagram for object-oriented programming stuff, and probably an example we will do. I might change and do a different example. Cars are a very common example. So we have like a generic car that has some traits that we need in our program, such as a video game program. Yeah, I think that's the one you'll do in the SDEV 140 class when you get to that. And that particular one in that textbook is a car example, and it has things like accelerate and decelerate and the basic things. And they took the graphics out, but that example is almost copied directly from the example of how to use Pygame, which is a popular game engine for writing games in Python. So for a racing game, you would have a car object. And then you'd have different types of cars. So any car is going to accelerate and decelerate, but different types of cars, like a sports car or a minivan, or you got a sports car or a truck or a van, would have different acceleration and deceleration. But then, like vans, we could split those up into more detailed versions to work into a video game per se. The full-size work vans or a minivan, and all the details work in. But I like to start with this diagram. You can see our diagram for object-oriented programming matches how we diagram the tree of life, which is the prime example of how humans naturally categorize things. So that's our big advantage with object-oriented. We get to think like a human. With the connections. When we put this together, that's still a piece of computer code. So inside of that circle, it's still the thinking logically, putting together algorithms. But when we build those pieces and put them together, we get to think like a human again. Or Joe mentioned Windows. That's one, the graphical user interfaces. We could do them without object-oriented programming, but it's a lot more work. So interfaces, we have things like buttons, or I can use HTML. Everybody in here I know knows HTML. Our HTML forms. We have our basic form input, right? That's our top level object. We have that input, which just, remember, if we don't put the type attribute in our HTML, we get a text box, just our most generic one, but it gives us a space to input text. But we can make more detailed versions of it. We could make a number box, which is just like a text box, only it has the restriction that we can't type letters in there. We only put numbers in there, so it's a more detailed, specific version of it. Or our checkbox, our radio inputs, which are kind of essentially types of checkboxes. They're very similar, just one's square, one's round. And all those different types of inputs are refined, more detailed examples of the overriding HTML input element. So we end up with that same structure when we start diagramming the connections between them. And things go back upwards. So our natural categorization, way we do things and categorize things for humans, includes our three main concepts. We're going to talk about them in detail, but encapsulation means everything. It has everything it needs. Like our life form in general, that includes everything we need in order to describe something as a life, to consider something a life form. And then other stuff inherits those traits. So like eukarya and then mammals and then humans inherit everything that it means to be a life form. So going down this way, going down our tree, we get stuff from the level above. And then the third concept we're going to talk about is going the other way. It's a big word for a simple concept, but polymorphism means one thing can behave as another thing. So in the case of the tree of life here, because that's a good analogy that most of us are familiar with, just because we're living things and surrounded by living things. If we needed any random life form, an E. coli bacteria is a random life form. So an E. coli bacterium is polymorphic to a life form in general. It can behave if all we need is a random example of a life form. So could an elephant, right? If we just need any random life form, an elephant would work because it inherited all those traits of what it means to be a living creature, a life form in general. So it's our natural way of categorizing things. I like to start with these two pictures to show that main point and that big advantage. It's better for the human because after we write our code in little sections, it's a little bit more refined than modularizing our code and putting together functions. It's actually a whole lot more refined than that. But once we get those sections together, they interact with each other the way the human mind naturally works, the way the human mind naturally wants to put things together. So that's our advantage for it. I'm going to erase these pictures. Hopefully that is okay if I erase them. And hopefully that kind of got us started here, because now we need to talk about the details of how we do this when programming. Hopefully that encouraged you about the advantages of it. Or what's going to be in the assignment, the one we're going to actually do this week. Instead of having a bunch of text files with HTML code that are all different things, we're going to make an object we're going to make a page object that has everything it means to be about a web page on our site. It has the nav bar, the copyright information, what it means to be a page on our site. And then we'll make more detailed examples of that page, of what it means to be a page. Like a home page is more detailed than just the generic what it means to be a page, or our order page, and build up our whole site that way and categorize things that way. It's a way of categorizing and putting together our code that gives us a great many advantages. So we will see that soon. But I like to start off with jumping ahead. I know I threw in some big words that probably seemed out of nowhere and left computer science altogether, but I like to start off with talking about the advantages of what it's going to be and what we're going to get from it. So I'm going to erase this as well. That's with those pictures, the advantage is we get to think like a human again. After all that work of learning to think logically so that we can put algorithms together that a machine can work with, we can turn around and actually think like a human again and get things done in a way that comes more natural to us. So there are three key concepts in object-oriented programming. And I already used all three words. So our three key concepts are encapsulation, and normally, like if you were taking one programming course at a time instead of three, the first programming course you would study most and practice mostly encapsulation and get familiar with that before moving on to the other two concepts. And what that is everything needed for the object is included in the object. I have several more analogies coming later, so hopefully clear this up. We're going to take a while and talk about it at length to make sure it all makes sense, because it is something that takes practice, and getting practice over time, letting knowledge sink in and practicing more. That's something that doesn't really fit in a classroom, right? we're on tight time constraints here, so we have to go over the concepts, and hopefully they're still in the back of your mind somewhere once you've had a little bit of practice and the stuff kind of sinks in a little bit better. So encapsulation, I'm going to say everything needed for an object is included in that object. So I was in that quick diagram, I was drawing circles, little bubbles. So everything that we would ever need for working with that object would be in that bubble that was drawn. We'll see the technically correct diagrams before long. They're squares, rectangles, but it's still the same idea. Everything that's needed would be listed out in that bubble. So everything we need is included. And also that includes some protection, ideas of protection for it as well. We'll see that here shortly. Our second key concept is inheritance. And there's different terminology. I'm going to go ahead and start using some of the terminology because I need to, but it's 2 more pages before I'll actually list them out directly in the notes. So one of those terminologies is parent objects and child objects, or parent classes and child classes. And we'll talk about the difference between classes and objects soon too. That's another thing about this is it's hard to get a good starting point because it's a full picture. It's all enclosed there. So we kind of have to jump in the middle and expand outward. It's hard to find a good starting point for object-oriented programming without jumping ahead a little bit. I'm going to use the parent-child term first. So, because that works with the word inherits, right? When we use that in our normal lives here in America, people have kids, people are living, they get a job, save up a bunch of money, buy a house, and accumulate wealth over a lifetime. And then when they pass away, their children inherit that. So the children get what the parents accumulated, and then they work jobs and build up more wealth and add to what the parents accumulated. So kind of the same thing here. That's why that terminology is very popular. A child class can get everything encapsulated in its parent class and expand on it. And I'm going to put and expand on it. We almost, in parentheses, we almost always do that, but sometimes it's just a naming thing. It's like the parent might not have a very good name that makes sense with what our algorithm's doing. So we just make a child that's exactly the same and give it a different name so it makes more sense with what we're doing. That's a very common thing to do as well. So encapsulation that's like in that tree of life I drew a moment ago, the bubble around life form, that has everything that it means to be a life form, but none of the details. It doesn't have the details of what it means to be like an E. coli bacterium, or the details of what it means to be an elephant. Those get added later as layer after layer after layer of a child of a life form inherits everything that it means from the layer above and then adds more details to it, expands on it. And our third key concept in object-oriented programming is polymorphism. a really big word for a really simple concept. If we look back at the root of the word, I guess that's a common thing when learning things, is what the word means. Poly means many, and morph means shape. So that word means many shapes. And that's the ability of one object to behave as another. Using the parent-child terminology to relate it to try to create an analogy for just average American life that you would think of is, well, parents and child probably living in the same house, right? Parents and children live in the same house. And it's the parents' house, so they're the ones that really should have control over it, right? In particular, what I was thinking of is having the key to the door. They're the ones that decide when the door gets locked or unlocked. But that child has that behavior as well, right? The child probably has a key to the door, so they can unlock and lock the door to the house just like the parents can. So they have that ability, in the case of children in America, having a key to the front door so that they don't have to just ask their parents to lock or unlock it every time. The child can behave in the same way its parent can. It has that same ability. You can fill that in. We'll see this with more explicit examples later. But an extreme example with programming is our objects that we put together to program programs with are going to have functions built in. And just because that function was built for a specific purpose doesn't mean that's the only purpose that function can be used for. So an extreme example, one that we would probably never use, just to try to explain polymorphism, getting away from the direct parent-child thing, is if we had an object that was set up to do statistics, or in particular take averages. You know, when we find averages, what do? We add up all the numbers and then divide by how many there are. So if we split that up into tasks, you know, so the nice form of designing our functions is one task for each function, or each function carries out one task. So we have two tasks. Add up our numbers and then divide by something. So our object for finding averages would have a function in there that adds a bunch of numbers together. So we would probably never actually do this, but in theory, at least, we could use that function anytime we needed to add numbers together. And that's an extreme case of polymorphism. That's not what that object was created for, but it's something that that object would also work for, because it has a function that would add numbers together. So anytime we needed to add numbers together, we could just call up an instance of that object and use that function to add numbers. We usually don't get that extreme in it. When we see some examples here in a moment, they'll make sense. So this is where, like your SDEV 140 class, we'll be going over these things in detail soon. And typically in that class, your homework is mostly studying encapsulation. Getting practice at putting everything that object needs inside of that object so that it can be reusable in multiple situations. And polymorphism, so it can also maybe leave it open to be used so that those behaviors can be used elsewhere if they would fit. And talk about those. And then in the language specific course, you get a lot more practice with these three concepts and introduce interfaces and abstractions. Might work with them a little bit, but it's mostly an introduction to interfaces and abstractions and kind of what's going on with those. And then the advanced classes, my original plan was to actually get practice applying interfaces and abstractions and namespacing, things like that. So I had to back that off, and we're going to do back it off to more of an introduction thing. But our textbook was kind of put together that same way. So those of you who read the chapter already, or if you're getting ready to read the chapter, it's probably going to happen then. But while reading that, you were probably quite confused because it did the key concepts very quickly, like a review section, and then it jumped into the textbook jumped into some advanced stuff fairly quickly. So it might have been confusing. So I want to clear that up, but we're going to treat our assignments and examples more like this key introduction level, because that's where 3/4 of the class is. Actually, it's 6 out of 8 people are in all 3 classes. Some can't quite make it here on Tuesday and Thursday afternoon, so we don't see them quite as often, but they're in the same situation. So encapsulation is going to be our big focus, and maybe a little bit of inheritance and polymorphism. But because of all that other stuff that was in the textbook, for those who have read it, or those who are getting ready to read it, I do want to talk about those other things and kind of clear up what's going on with them. Is it okay if I erase the board? Because now as we talk about encapsulation, I'm going to draw some pictures, and I need a lot of space for doing that. I don't hear any objections, so I'm going to go ahead and start erasing. And yeah, it's a methodology we use to put things together. And I have an example that you all will be very familiar with of what I mean when we say put things together. Because as we continue talking about this, there's a lot of generalizations that almost are going to make it sound like we're not actually doing anything with them yet. And that's one of the things is with object-oriented programming is when we build our classes, a lot of times we're not doing anything with them yet. We're just planning on doing things with them later, but I have a good example of that later. Four pages further up in the notes. So there's quite a bit to talk about here. What time is it? 3:05. Okay. So encapsulation, that's our big focus. That's the introduction. That's where we start at, is just making those bubbles. How do we include stuff? So that's our big focus, but that is fine because in PHP, encapsulation will show our primary use of objects, the main thing we'll probably want to use objects for in both full stack development or producing CMS sites, content management services. So just covering encapsulation will show what we actually, the biggest thing we want to get out of PHP. So yeah, that's what I was saying. What we're going to talk about this week are probably the two, in a sense, the two most important things we're going to see this whole semester. And as far as like making you happy about what you do with your code, making you happy about putting this stuff together. Because it's going to address a question that shows up in every single version of the SDEV 153 class I've ever taught. I believe it was you that asked this, Joe, the first 8 weeks, Joe. And that had to do with when if you add another site to the page, right, we have maybe our original site. I'll just draw a quick picture, had 3 pages on it. So they're on our page, we have some big title at the top, and then, well, maybe down the side, we have a nav bar, the navigation bar that has the links to those other 3 pages. And in SDEV 153, we're writing all that as HTML code. Each one's an a file of a text file with HTML code written in it. And if you have another idea and want to add maybe 2 more pages to your site, does that mean you have to come through and add that on every single file? That question gets asked pretty much every time I teach the course. And back then it was yes, right? Because everything's a unique file. We have to type it all up. We can at least copy and paste, which helps a little. But it's still, we have to, if we had 2 more sites, we have to go back and add those links to those sites in the original 3, and then on those other 2 sites as well. So we keep having, it's more and more work to expand it. Every time we make an expansion, it increases the amount of work we have to do in order to make another expansion. So when we consider encapsulation, we can include what it means to be a page. I guess I could have left that up there. So have the title, like the one we're using for class example, kind of looks like this, right? Did I put a footer in the bottom? I can't remember if I put a footer or not. I haven't looked at it since last time we did an example in class, but this part changes, but all of this stuff is the same on every single page, right? So that is what it would, all of that stuff is what it means to be a page on our site. So we want to encapsulate that and include that core meaning of what it means to be a page on the site. And then we can expand that to a child class, and the children of that, what it means to be a page, would inherit all of that aspect, all of that stuff, our titles, our links, the stuff in the head tag, because we'd probably link to the same style sheet everywhere, put the same metadata on all of it. All of that is just what it means to be a page. So we can encapsulate that in the parent, and then the child classes just add in the detail for the content section. It makes our work a lot shorter, right? Because then to add another page, well, we just make another child of this, so it inherits everything. And then we only have to add the link in the parent, and everything inherits that other link. So we don't have to keep doing it over and over and over and over again. And that's pretty much what the assignment's going to be for this week. And for considering how to encapsulate things, I like the donut picture is what I call it. So we have 2 circles. So this is kind of our object. And then somewhere out here, we'll have the client that's actually going to use that object. And in the inner circle, that's our properties. That's the things about the object, all the properties it has. And the outer circle is the behaviors. How it acts, what it can do. So our technical terminology for that, the properties, that's our data, what we would store in variables, right? So we have some technical terms. So in object-oriented programming, our variables inside of their objects, because when we go to use these, we still need regular code to put them into action. So what's included, we want to give it a different name than variable, because we'll use variables when we actually instantiate them and use them. So in our objects, we call these data fields. And that's like a variable. Because when we design our object, we don't know what the data is going to be, right? we just need, so we make a space for the data, which is essentially a variable. You're going to think of it that way at first, but we'll call it a data field. It's just a place for our data to go. Right? I mentioned an object that finds averages. Well, when we design the object, we have no idea what numbers the user wants to take the average of. Right? It's an object that includes or encapsulates everything it means to find an average. So the user is going to feed in a bunch of numbers, and we don't know whether the user wants to find an average cost, an average height, average baby weight, average hair color. There's a lot of things we could find the average of. And when we design our object that finds averages, we don't know what the user is going to use that for. So all we can do is leave a spot for them to give us data, leave spots for them to give us the data they want to find the average of. And then the behaviors would be the functions to find that average. One function that adds numbers together, however many the user gives us, and another function to divide by how many the user gives us, the stuff to find an average. And that's a behavior, which we would put into functions. And whenever we have that in object-oriented programming, we typically refer to them as methods. As far as technical terms, we do most stuff in object-oriented programming anymore, because as soon as computers could keep up, which was about 1984, 85 or so, just quickly took over. So 36 years later, our entire working careers into programmers have done this their entire working career and retired now. So it's well worked in. So these terms might be used interchangeably. Sometimes you might have something that's technically a variable and hear somebody call it a data field. Or very common is the words methods and functions are used interchangeably. Because we're writing in PHP. What's our keyword to create a function? We have to put the word function there, right? But when we do that in an object, we're going to refer to it as a method, even though our keyword is the other one. So when we're talking to other programmers, like on other members of a team working on a big project, there's a good chance we're just going to say function instead of methods. But technically, we would say data fields for the variables and arrays and things we're going to use, spots to put our data, and methods for the behaviors to functions. And then that gives us sort of a layer of protection. Hopefully this color is going to show up a little on here. I'll try the red one. So the client, to protect the data, the properties of our object, we don't want to give the client direct access to it. So the client can access the outer circle. The client can access the behaviors, and then the behaviors have access to the properties. So you want to keep something like that in mind when encapsulating things. I'll put another example. Yeah, I guess I'll be using, we'll be kind of looking at an animal example at some point this week. If you haven't realized it yet, this lecture is going to drift over into Thursday before we get all the way through it, all the way through this set of lecture notes and get into the web page example. There's going to be a basic example coming up first, and it's going to be an animal example. So with this picture on the animal thing, the animal example I always use, for example, so I'm going to erase this one before I erase the other one. For a little bit of code, is just to quickly introduce this stuff. Our animals are all going to have a name, an age, and a sound that they make. And that's the properties about them. That's what they have. So like a dog animal might be named Fido, age 5 years old, and make the sound woof. Or a cat animal would be named Fluffy, age 1 year, and makes the sound meow. And we'll fill that in at runtime. Those are two examples that we'll probably use when we get there. And then that data is protected. It's all nice, safe, and secure there. We keep that private so that nothing from outside our object can access it. And then in the outer circle, we'll have, we might need a way to access it, so we'll give it behaviors that would work. So one behavior might be to get the name value. And if the client out here asks for the get name value, the get name value hops into that inner circle to grab the property, the data itself, and then sends it back to the client. But it has to pass through this circle to help protect our data. Or get age would be another behavior to work with that data. Or get sound, but it would make more sense from that word to say make sound instead of get sound. And that kind of does the same thing. When the client asks for that behavior can reach our private data. So these are all public. This public make sound behavior can access our private sound data and bring that back out to our client. So I like this picture for how we want to think about things when we encapsulate them. Everything the object needs is included or protected. And another analogy that I've heard over the years that a lot of people feel like it makes sense to them has to do with language, like our talking language, speaking language, writing language, normal human language, not programming language. You think of objects like nouns. It's the subject of the sentence. And the subject of the sentence, when we have an interesting sentence, that subject is going to have some descriptive terms about it, a bunch of adjectives and adverbs. And it's also going to have the predicate of the sentence, the verbs that noun is actually doing. So with encapsulation, you think of it, instead of separating that, our object is like the noun, and every descriptive term that we could put with it, every adjective and adverb, that's a property about it. They're already included with that. Wherever, or any verb that noun could carry out, anything that noun could do would be a behavior. And it's already included with the original word, so we don't need separate words brought in order to make sentences. So in languages, it'd be kind of like hieroglyphic sort of languages, the pictorial-based things, where the picture represents the object, and then modifications to that the picture of that object explain details about it or what it's doing in that particular case. So it's some people's minds just go very well with language. So I wanted to throw that analogy out there because it's a common one to hear. But there's different ways to think about it. Just want to remember that core idea that everything this object will ever need should be included in it. And what time is it? 3:21. We still got a little bit of time. And along with that is a principle. I'm going to erase this example. Is that okay? I want to leave the generic picture there. And there's open here, the open close principle. Anybody that's planning on continuing to a 4-year degree, 4-year computer science degree or something, this one is something you'll hear over and over again as you proceed through the degree program and deal with objects in different situations. Back to the open close principle, and that is objects are open for extension which is inheritance, the thing we're going to talk about in a moment. So it's kind of back to that. There's not a good place to start talking about this. We're kind of in the middle and we have to refer to things before we actually explain them. But objects are open for extension. So we have all these properties and behaviors that define what it means to be that object. We can make a child class and add more properties or more behaviors that make a more detail and add details in, some finer details of what it means for that object. So open for extension, but closed for modification. And that's encapsulation. Like capsules in that word, right? So think of a time capsule. We take a whole bunch of stuff. So using today, we take a whole bunch of things that would represent what it means to live in 2021. Right? Well, we throw in, probably throw in a couple phones, some tablets, throw in some masks, newspapers if we can find them. I think most newspapers have gone to websites. That's kind of hard to put in a time capsule. But we'd take a bunch of items that represent what it's like to live in 2021 and put them into a capsule and then seal that capsule up. And usually with a time capsule, we bury it. And at some point in the future, somebody can dig that capsule up and see those objects of what it meant, that represented what it meant to be alive in 2021. So capsule, that word's included there. So you can think of it that way. Everything that we'll need in order to write a program. What data are we going to need? What functions are we going to need? What variables do we have, and what functions or tasks are we going to have to process those variables? We put them together into this capsule and then seal it up. It's closed for modification. Once it's put together, we don't open it back up. We put it together, seal it, and leave it sealed. If we need to do anything else, we extend it. We make a child of it that inherits everything it has, and then add details to the child because it hasn't been sealed up yet. So 330. The next thing on my notes is inheritance. And I wanted to jump over and do some syntax examples when we get to inheritance, after we talk about inheritance. Then we have something to put together. So that seems like it might be a good starting point. That way you can think about the encapsulation, the idea of enclosing everything, including everything we need, and sealing it up so that, it does involve a lot of planning ahead. So we'll start with that there. And I'll go ahead and put up the list of terminology. that will be used, because so far I've been saying parent and child over and over again. But that's not the only terms we'll use. There's different terminology that you might hear. You might hear it called base class and derived class. So a derived class inherits from the base class. Another very common one is superclass, and that is connected to a subclass. So a subclass inherits from a superclass. In particular, subclass fits nicely with that biology diagram I drew, the tree of life thing. Because a mammal is a subclass of a eukaryote. A eukaryote is a subclass of a life form. And an elephant is a subclass of a mammal. So that's a terminology that's used a lot because it fits with that natural categorization that humans do, the super and sub. It shows up in a lot of places, like with our numbers, superscripts or subscripts, and those words tend to be used a lot in English. So might use those, and a subclass would inherit from a superclass. And the third one that I've already been using, because it fits nicely in American culture, the parent class is going to be used with a child class. And I wanted to make sure and express this terminology explicitly because they're used interchangeably. We might say base class, we might say parent class, either one. But like this whole row is, we would not use parent class and derived class together. So if we're talking about, if we say base class, then we would say derived class to go with it. We wouldn't say super class and child class. So we don't mix them that way. So it's always pairs of terminology that go together. So you want to be careful about that. But we have options on which terminology to use. And then the ones I pointed out here, variables. We're going to rename those data fields. Which we talked about it earlier today. Relational databases are a prerequisite for this course, right? And that word probably should have shown up in that class, right? That was a big deal there. The data fields. And next week, after we've talked about object-oriented programming and review databases, we'll talk about tying them together. Because it's not just random coincidence that that term shows up in both object-oriented programming and relational databases. Sort of a hint of how these are going to tie together starting next week. And functions, we're going to refer to those as methods. So then, yeah, so it's 3:30 now, yeah. So then on Thursday, we can jump in and talk about inheritance and polymorphism. And then some stuff about abstraction, abstract classes and interfaces. Because the book talks about those at length. So if you haven't seen them before, it's probably very confusing because the book doesn't really introduce them either. The book seems to presuppose that you already know about those. Then traits and namespaces, those are in there as well. Gonna have some examples, more stuff, and then finally back to our final example. But I wanted to stretch this out and talk very thoroughly about object-oriented programming because it's kind of an important thing, and you want to get a good feel for it, which getting a good feel for it means practice. And not just practice, but practicing it, having a little time for it to sink in, and then practicing it some more. So it's a skill that will develop over time. And time is something we don't really have in a classroom setting, right? We are very restricted for time here. So I want to make sure and go over it very thoroughly so that when you do have time or over time as you're actually doing it, the concepts are all still in the back of your mind somewhere so that a better understanding will hopefully develop as you do it more and more. Not that it's super confusing. I mean, we'll be making I don't expect anybody to have any trouble making our objects or homework this week. For this class or your other programming courses, because it's that first note I made. It's where we get to think like a human again, but it's a skill. So as we do it more and more, it will get better. So over time, what we don't have time for in the classroom is lots of practice with time for the knowledge and experience to sink in and get a lot of improvement and get better and better at it. But as far as putting objects together, that's not going to be any problem at all. It's thinking like a human again, so it's going to come very natural for you. But that brings us up to about 3:30, which leaves us an hour and 20 minutes of time for lab. So remember, well, way back in the beginning of the class, I was writing out that list of the amount of time that to be expected to spend in a class. And that's kind of what ours is set up for, right? Well, it's an 8-week class. So what I wrote on the board earlier was the old 16-week model. So instead of spending, those were always an hour and 15-minute classes. So it actually, we say 3 hours, but it actually turned into 2.5 hours. So now that we're in 8 weeks, it's 2.5 hours of lecture, but with Skip making the schedules, there's always lab time involved as well. So we want to make sure that we have time to practice when I'm sitting here available to help if you have any questions. Because it's 4 weeks in, and I know most of the class is taking a fairly heavy load. Oh, sorry. I forgot to turn my phone down. There we go. Sorry about that. I know everybody's taking a heavy load, so you probably have a lot of work to do. So now is a good time to split off. We still have about an hour and 15 minutes of lab time. And as normal, I'll be sitting right here by my computer, or I'll keep my setup. I'll be sitting in my office, not in my gym, where there's a more comfortable chair. But I can jump back on my computer. I'll keep the video set up here, so I'll be back on here in a couple of seconds if you have a question. Before we split off, does anybody have any questions?
Not on this, but if nobody else has anything for you, I got something I want to run by you real quick to see if my thought process is straight. It's more of a JavaScript question, but I'm just trying to think of if I'm thinking the right way on trying to debug something. Okay.
Yeah, so I'll go ahead and stop the recording. And as far as lab time, well, that's shown up before. I need to check for PHP questions first, but yeah, otherwise that was it for today. And we will pick up from there and finish the lecture on JavaScript and get into examples of it on Thursday. Everybody have a good afternoon. If you have any questions, and yeah, like you may have just heard from Joe, I also know JavaScript and Python, so those taking multiple classes, if you have questions from those other classes, I can help with those too. So I have lots of open time on my schedule. So any questions you have, just let me know. Otherwise, everybody have a great day. I will see you on Thursday. And stop the recording.